You know, all those amazing AI tools that we're all using now? I mean, everything from chatgpt writing an email for you to an image generator creating some kind of masterpiece. Well, they all run on a hidden engine, an engine that's incredibly, unbelievably power hungry. We get to see all the magic right on our screens, but behind that curtain, there's a physical world of hardware that's working at a scale that is just, it's really hard to wrap your head around.
Right. And this is where things get really interesting. See, the whole AI revolution isn't just about some clever software. At its core, it's a battle over raw materials and very real physical limits. It's all about who can get their hands on the specialized hardware that makes any of this possible. And that creates this super intense economic reality, where controlling the supply of these parts, well, that pretty much means controlling the future of AI itself. And when we talk about resources, let's just start with energy. Look at this number, 1,287 megawatt hours. That is the staggering amount of electricity it took just to train one single kind of early AI model like GPT-3. To give you some perspective, that's enough to power over 120 American homes for a whole year. And honestly, the models we have today make that number look tiny.
So what is going on here? What's driving this incredible appetite for power? What is this specific piece of hardware that's at the center of the AI universe? And why is everybody so desperate to get their hands on it? It's a totally fair question, right? You probably have a pretty powerful computer sitting on your desk. So why can't it run these massive AI models? Well, the answer comes down to a really fundamental difference in how computers think, and it's all about two very different kinds of processors. So let's meet our two main players in this story. You've got the CPU, which is basically the brain of your everyday computer, and then you have its powerful, super specialized cousin, the GPU. Now, they both process information, but they do it in ways that are almost polar opposites. Okay, think of it like this. A CPU is like a master surgeon. It has just a few extremely powerful cores, and it's perfect for doing one really complex operation at a time with incredible speed and precision. A GPU, though, a GPU is like an army of medics. It's got thousands of smaller, simpler cores. It can't perform complex surgery, no way, but it can handle thousands of simple jobs all at the exact same moment. So your CPU, it's a generalist. It's built to be a master of all trades, quickly juggling everything from your web browser to your operating system. It processes instructions one after another, in a line, sequentially. And this makes it amazing for general computer use, but it creates a massive, massive bottleneck when you throw the kind of math that AI needs at it. And this is exactly the kind of problem a GPU was born to solve. I mean, they were originally designed to render graphics for video games, which, if you think about it, means calculating the color of millions of pixels all at the same time. Turns out that parallel architecture is perfectly suited for AI. Training an AI model means doing billions of nearly identical calculations over and over again, and a GPU's ability to do all of that in parallel just makes it exponentially faster than a CPU for these very specific tasks. But wait, the story doesn't even end there. The GPUs that are powering this AI revolution, they're not quite the same as the one you might have in your gaming PC. Oh no. They've evolved into these highly specialized machines with hardware designed for literally one thing, making AI go faster. This is it. This is what we're talking about. This is an NVIDIA data center GPU. It might not look like much, but this card, and thousands of others just like it, are the real engines of modern AI. And they are packed with technology that goes way beyond just simple parallel processing. And right here, this is the secret sauce, tensor cores. The best way to think about these is like a specialized GPU within the GPU. They are dedicated little units that do one particular thing exceptionally well, the very specific kind of math that lets an AI find patterns and make connections in huge seas of data. This gives these GPUs an absolutely incredible speed boost for AI calculations that normal cores just can't match it. And you can just see the blistering pace of innovation right here. The first generation with these tensor cores, Volta, gave a 5x speedup. Just a few years later, the Ampere cards offered up to a 20x speedup. And now with the latest Hopper generation is promising another gigantic leap forward. It's this exponential growth in computing power that has really enabled the AI explosion that we're all living through right now. But all this incredible power, it comes at an incredible cost. It reportedly cost over $100 million in compute resources alone just to train a cutting-edge model like GPT-4. This isn't just about writing some software. It's a massive capital investment in hardware and power and in infrastructure. So, this intense demand for a very specific, very expensive piece of hardware has created a global bottleneck. We're basically in the middle of an AI gold rush, and GPUs have become the new digital shovels, and there just aren't enough of them to go around. And this scarcity creates this huge ripple effect across the entire global economy. You've got tech giants buying up the supply years in advance, and what does that do? It drives up prices, not just for AI companies, but for pretty much everyone. The components in these data center GPUs are also used in consumer electronics, which means the AI boom could actually make your next phone or laptop more expensive.
So, at the end of the day, what this really means is that the hardware bottleneck is creating a very clear divide. The companies that can actually get a steady supply of GPUs are the ones who can innovate and dominate the market. And those who can't, well, they get left behind. Access to hardware is now one of the biggest factors in determining who wins and who loses in the tech industry. But here's the thing, even if we could somehow magically produce enough GPUs for everyone, we'd still be facing an even more fundamental challenge. All of this incredible computing power comes with an equally incredible thirst for electricity. I mean, the difference in power consumption is just stark. A standard CPU might pull around 85 watts, but an NVIDIA A100 GPU, one of the workhorses of AI, can consume 400 watts when it's running full tilt. Now multiply that by the tens of thousands of GPUs needed to train a large model, and the energy numbers just become astronomical. And here's where all that power is going. Look at that huge chunk. Over 62% is used just for training the model. That's that initial brute force process of teaching the AI. Now, actually using the model to get a result, what they call inference, takes a lot less power, but that initial training phase, that is by far the most energy-intensive part of the whole AI lifecycle. The scale of this problem is truly global. Right now, data centers already consume about 1% of all electricity on the entire planet. With the explosive growth of AI, some projections are showing that figure could double by the end of the decade. That trajectory is, well, it's just not sustainable. So, can we build a more efficient brain for AI? Well, the industry is focusing on three key strategies. First, creating even more specialized hardware. You have chips like Google's TPUs that are custom built just for AI, which makes them way more power efficient. Second, moving some of that processing to the edge, doing the calculations on your local device instead of sending everything to a faraway data center. And third, kind of ironically, is using AI to manage the data centers themselves, optimizing things like cooling and workloads to save massive amounts of energy. This AI revolution is being powered by a very real physical revolution in computing hardware. This hardware has unlocked things we could only dream of just a decade ago, but its demands for materials, for money, and especially for energy are pushing our existing systems to the absolute limit. And that leaves us with a really critical question. AI is creating a brand new world, but can we actually power it without breaking the old one?